Hello, my name is Yuri Kasser, and I am one of two creators of the novel Skoltech Anomaly Benchmark, or in short, SKAB. In this video, I will try to describe the motivation, features, insights, and details regarding the SKAB. To begin with, let's shortly look at the two main sub-problems of the anomaly detection problem. So, the anomaly detection in sequential data is often divided into two specific problems: outlier detection for point anomalies and change point detection for collective ones. Specific benchmarks are typically used to evaluate the algorithms that solve each of the problems. The first problem we also often call binary classification, and it is the problem of finding point anomalies. This problem can be also called clustering or one-class classification. Most anomaly detection benchmarks and techniques relate to this type of problem. The second one is the problem of finding collective anomalies, often referred to as a change point detection. The definition is following. Change point detection refers to the locating points in time or position where some aspects of the data of interest, such as scale or distribution, changes. But what is our motivation to create one more benchmark? Though the anomaly detection problem is crucial in many industries, there are just a few public benchmarks. Unfortunately, most of them have some downsides, like an enormously low number of benchmarks with collective anomalies and anomalies representing industrial faults and failures, or poor description. Among others, a significant challenge for proper algorithms evaluation is a lack of change points. Moreover, a lot of benchmarks contain synthetic data instead of real-world data or univariate time series. A major drawback is having obvious anomalies detectable with simple one-liners or simple rule-based heuristics. So, our goal was to develop a benchmark with the following properties: applicable for testing anomaly detection algorithms in the field of faults and failures of technical system. Both outlier detection or binary classification and change point detection problems must be involved. It is also important to prove the relevance of the benchmark by proposing and testing baseline algorithms. The benchmark should be easily accessible. So, the data for SKAB was collected using the specific testbed shown on the slide. Generally, the testbed is designed for approbation, verification, and validation of new technologies related to the industrial IoT in order to determine a set of scientific theories, algorithms, and practical tools for applying these technologies in actual industrial tasks. We focus on first three systems in order to collect data in various modes and demonstrate solving technical system fault detection task. Water circulation, control, and monitoring systems are designed to simulate a water supply system, but operate a closed-loop water pump, control it, collect and monitor data for further processing and visualization. Each file in the benchmark contains data acquired from one experiment and one anomaly with its beginning and ending. In most cases, the anomaly is represented in files as follows: 10 minutes in normal, healthy, or fault-free state, 1 minute of transition state, 5 minutes of steadily anomalous state, 1 minute transition mode from anomalous to normal, and 3 minutes of the normal state. Each file is structured in a form of a matrix containing more than 1,000 rows and 11 columns. Rows are related to the timestamps, while columns correspond to the features or process variables and target. Description of the features and target columns are shown on the slide. The details regarding the anomalies you can see now. All the anomalies in the dataset are related to the industrial faults and failures by the application domain type. A description of each anomaly type by the number of points and total number of anomalies for each type are presented in table on the slide. We also propose evaluation metrics and algorithms for both subproblems. For benchmarking and outlier detection problem, binary classification metrics can be used. To provide clear comparison, instead of commonly known precision and recall metrics, we use a single metric called F1 measure. Additionally, we use two metrics known as false alarm rate and missing alarm rate. These metrics are easy to understand and implement, and at the same time, they are popular in industrial applications. As for the change point detection problem, the mentioned classification and performance metrics do not consider time and do not reward the early detection of the anomaly. So we suggest using the Anomaly Benchmark scoring algorithm and quite simple average detection delay metric. We propose the first version of the SKAB leaderboard for the 11 selected well-known outlier and change point detection algorithms, including recurrent neural networks that are state-of-the-art in technical diagnostics. Additionally, we use perfect detector and null detector for better understanding of the possible best and worst case scenarios. A Python implementation of the evaluated algorithms and experiment setup are available in the GitHub repository. Their scores, according to the previously proposed metrics, both for outlier and change point detection problems, are provided on the slide right now. All results are calculated for out-of-box algorithms without any hyperparameters tuning, which can be used for further results improving, by the way. These are the leaderboards for SKAB version 0.9. We're going to contribute to this leaderboard by adding more algorithms with their scores. The up-to-date version of the leaderboard will be publicly available in the repository. The leaderboard will be updated in the future for the new SKAB versions with benchmark version indicate. One more important detail about the benchmarking process. There are three possible ways of fault-free or trained set selection. Using separate file with relatively long fault-free operation mode, we provide this file. So algorithms are once trained and applied to all data sets. Second one is using the beginning of each data set as a fault-free mode. So algorithms are once trained and applied to all data sets. Or the third option is using the beginning of each data set as a fault-free mode. So the algorithms are trained and applied using every single data set. For the leaderboard results right now, the calculation, we have, for the leaderboard results calculation, right now we have selected the third way using the first 400 points of each data set as a fault-free trained set. So the outcomes of this work are shown in the left part of the slide. We also currently have papers under preparation. All information about the Skoltech Anomaly Benchmark, supplementary materials, benchmark using, and experiments repeatability provided in the repository. For direct link, you can use QR code on the slide. Thank you, and we hope our work will help your research.